So, I had shown you a number of experiments to demonstrate how a magnetic field exerts force on a charged particle or a current element. But if you have a current loop where the direction of current is changing and finally it makes a loop, or equivalently you have some material, a small magnet or a pin, there the force due to magnetic field will be calculated or will be obtained in a slightly different fashion. The first thing which I would like to mention is a magnetic field will exert force on such a system where you have either current loops or you have neutral materials in which you have atomic currents only, like paper pins or magnets. The field should be inhomogeneous. Only inhomogeneous magnetic field will produce force on such an object, and to demonstrate that I have a very nice simple experiment. So, what it is? Let me first show the parts of this experiment. We have a spring balance, and this spring balance is graduated in newtons, and this red thing that you are seeing, that is the marker. So, it reads how many newtons are here. Weight is measured in newtons in this spring balance. From this spring balance, this magnet is hanging here through a thread. So, and some reading is there, 0.1 Newton. Here is a solenoid, and the two ends of the solenoid are connected to these two screws here, and we have connected it to power, DC power, through an adapter. So, here is the adapter, and when I put this on, the power will go and there will be a current in this solenoid. So, this is the setup. This current produces a magnetic field which will be almost uniform in the central part of the solenoid, but then it will diverge from the end, and therefore, here the magnetic field will be inhomogeneous. The experiment consists of putting this magnet close to the center here on the near the axis, close to the axis, and then seeing whether what kind of force this current exerts or this magnetic field exerts on this magnet. So, we start. So, I put this thing here, and you can see that the magnet is close to the top of this solenoid where the field is diverging and therefore, is inhomogeneous, the magnitude changes, and you see the reading here, that red marker, what it reads, it is close to 0.1 Newton. So, that is the weight of the magnet and all these hangers and everything. Now, I am going to put the switch on. So, what happens? It has gone down, the marker has gone down. So, this magnetic field which is created by the solenoid has pulled it down. It has exerted a force in the downward direction, and that is why this whole thing went down. Now, let me change the height of this stand so that this magnet goes in the middle region. So, I am lowering this whole thing. So, I have lowered this magnet. Now, you can see where the magnet is, and if I put this solenoid, the magnet will be somewhere here in the interior, in the central region. Once again, you focus on this red marker and see what happens when I switch it on. Here it is, and you see the red marker has hardly moved anything. So, this magnetic field is almost not exerting any force on this magnet. I have another very simple experiment which will again demonstrate that an inhomogeneous field will exert force on such kind of materials. So, I have here a magnet, a cylindrical magnet. This is the flat face, which is one of the poles, and then I have a steel ball, and this steel ball goes and sticks to this magnet, but you can see that it is sitting at the center of this face. Now, if I try to take it near the edge, see what happens. I am taking it towards the edge and leaving it, and it comes back to the center. So, I take it to the edge and leave, and it comes to the center. So, there is a large force which is pulling it towards the center, and why that force is coming towards the center? Because the field is inhomogeneous in that plane also. If you look at the central part, the field here is strong. If you look at this part, the field here is weak. So, there is an inhomogeneity in this direction also. Indeed, there is an inhomogeneity in this direction. As you go away from the magnet, the field decreases, but this way also, if you go from the central part to the these edges, the field decreases, and this inhomogeneous field is responsible for pulling this steel ball towards the center. But why do I need that steel ball bearing? Can I put a copper ball bearing there, or an aluminium ball bearing there, or for that matter a plastic ball there, or a foam there? The behaviors are very different if I take different materials. Broadly, one can divide the materials in two categories: magnetically ordered and magnetically not ordered. Then in the magnetically ordered materials, you can have further subdivision: ferromagnetic, antiferromagnetic, ferrimagnetic, and so on. And in the not ordered systems, you have a paramagnetic and diamagnetic. So, in general, the paramagnetic materials, they get attracted towards the stronger magnetic field, whereas the diamagnetic materials, they go away from the stronger towards the weaker magnetic field side. We have and then we have these ferromagnetic or antiferromagnetic or ferrimagnetic material, that is ordered material. It is a different category, but let us first do an experiment to see the paramagnetic and diamagnetic behavior. In this experiment, what I have is a tub, and we have water in the tub, and then we have a test tube, and in the test tube I have put a vegetable oil, the oil that we use in kitchen, and this is just a thermocol to make it float in water. So, if I put it here in the water, it just floats with test tube remaining vertical. Then I have this magnet. In fact, 1, 2, 3, 4, 5, 6 magnets. but this whole thing will behave as a magnet, and this is just a handle to hold these magnets. Now I will bring this magnet close to this vegetable oil and see whether this vegetable oil gets attracted towards the magnet or it goes away. You see, it is going away, the separation is increasing. Once again, I keep it here in the middle, try to bring it at rest and bring this magnet close. And see, the distance is increasing, it is going away. Is going away. From the other side, see, it is going away, the separation is increasing, it is going towards right as seen by me, and if I bring it from this side, now it is going towards left. So, the vegetable oil gets repelled by a magnet. It goes away from the magnet. It goes from the stronger magnetic field side to the weaker magnetic field side. Such materials are called diamagnetic materials. This particular vegetable oil, whatever brand it is diamagnetic. Not necessarily all vegetable oils will be diamagnetic, but it is. Copper is diamagnetic, water is diamagnetic, and diamagnetic materials are materials made of molecules or atoms, the basic entity which does not have a permanent magnetic dipole moment. Each electron has a dipole moment because of its spin angular momentum, because of its orbital angular momentum, and then an atom or a molecule has so many electrons. So, all these magnetic dipole moments of all the electrons, they add up to give magnetic moment of that atom or molecule. If that vector sum happens to be 0, the material made of such molecules or such atoms will become diamagnetic and it will be repelled by the magnets. Paramagnetic materials are made of molecules or atoms which themselves have a permanent dipole moment. So, the total magnetic moment of all the electrons taken together, vector sum, that is not 0. So, such materials are paramagnetic materials and they are attracted by the magnet. They go from weaker field side to the stronger field side. I am still not talking of ferromagnetic materials like iron or nickel or varieties of alloys which are ferromagnetic alloys which are strongly attracted by the magnet. That is another category. I will show the behavior of a paramagnetic material in this same setup. So, now I have this copper sulphate in this test tube, powder, copper sulphate powder in this test tube, and again I make it float. Okay. So, this copper sulphate is in the test tube which is floating in water, and once again I can bring this magnet and see the effect. So, let us put it at this separation and see what happens. See, the separation is decreasing, it is getting attracted. It's coming towards the magnet from this side. It's coming towards the magnet. It's coming towards the magnet. So it's going in this direction. If I bring the magnet from this side, that velocity will be checked and it will reverse its direction and will come towards the magnet. Let's see. Yes, it has started coming towards the magnet. So, the copper sulfate and many such substances are paramagnetic in character. They have their atoms or molecules have permanent dipole moment, and from such materials you can also have ferromagnetic materials or magnetically ordered materials in which there are permanent dipole moments, and they interact with each other in such a way that neighboring dipole moments try to align with each other or try to just be opposite to each other and so on, and this ordering goes for a much longer distance. Then you get domains, and from that you get all kinds of ferromagnetism, antiferromagnetism, etc. Now, in ferromagnetic material, what happens? In such a material, the individual dipole moments of atoms and molecules, which are non-zero, they interact with each other in such a way that they align themselves parallel to each other. So, each molecule will try to align the neighboring molecule in its own direction. So, if you have two dipole moments close by, then they will become parallel to each other, and the third one becomes parallel to this, and the fourth one becomes parallel to this, and this way you get a domain in which millions and millions of these dipole moments have the same direction. So, that becomes a domain, and from such materials you make magnets. So, this is called exchange interaction, and the competing thing is thermal motion. Thermal motion is random, and it will try to randomize the dipole moments, and this exchange interaction will try to make them aligned. So, in this competition, if the temperatures are low, then this exchange interaction dominates, and if the temperature is high, then the thermal motion that dominates, and therefore, any ferromagnetic material will have a highest temperature up to which it will remain ferromagnetic. If you increase the temperature beyond that, then the thermal motion will start dominating over this exchange interaction, and this ferromagnetic domains, they will break, and it will become a paramagnetic materials, and that temperature is known as Curie temperature, and the next experiment to show this Curie temperature phenomena. So, here is the experiment, and we have this heater coil made of some alloy, and this coil is connected to the power source here. This is an AC power source, and we can change the voltage using this particular knob, and here is a bar magnet, and since it is a ferromagnetic material, it strongly gets attracted towards the magnet, and it just stays this way. Now, I will give it some voltage so that some current will go through this coil, and it will get heated, and then you see what happens when it gains sufficiently high temperature. So, I am putting the switch on and then increasing the voltage, AC voltage. So, the current is already going on and it is getting heated. and see what happens. Once again, so it has cooled down and again it has become ferromagnetic and it gets stuck to the magnet. Switch it on, increase voltage so that current goes through, it gets heated, temperature is increasing, and it leaves the magnet. So, once it attains this Curie temperature, these ferromagnetic materials become paramagnetic, and then there is not any strong attraction between the magnet and the coil.